So let's go now. Yeah. So hello everyone. I'm Miranda. I'm the PhD student of Miriam Veronica Chovanova. I'm going to present our work, Qtrits for Physics at LHC. Especially, we develop a quantum machine learning model based on Qtrits for anomaly detection in CMS data. So first of all, what's the LHC? The LHC, it's the Large Hadron Collider located at CERN, where they collide mostly protons at some detectors, as for example ALICE, CMS, LHCb, and ATLAS, to study our why not discover fundamental particles. So then, what's anomaly detection? Anomaly detection, it's the detection of anomalous events not explained by the standard model of particle physics, which is not only experimentally, but also computational challenge. And it will be intensified with the implementation of the next generation colliders, as for example, the HighLuminosity Large Hadron Collider. Leaving classical machine learning models or even quantum machine learning models based on qubits insufficient, and that's why there's people like us studying other possibilities like Qtrits. So why Qtrits? Maybe sounds crazy, but there's some advantages. For example, we have a higher storage capacity without using any advanced method of encoding. We can storage 1 bit per qubit, but using Qtrits, we can storage 1.56 bits of information per Qtrits. So we are gaining a storage capacity. Also, we have a richer set of operations, richer set of rotations, bigger hybrid spaces, and not as crazy as it may seem, as I said, and these two papers are the perfect example. For example, in the first one, they implement using qubits a quantum error code beyond the break-even, and in the second one, they implement using trapped ions a quantum Fourier transform algorithm using qubits, and they obtain very competitive and very interesting results. So it's not something impossible. So, okay, when you try to develop a new model, the first step is taking one good model as a reference, and that's why we took this one when they present a new type of encoding for particle physics, 1 particle per qubit, with great and very robust results. So we decided that this one a good model to take as a reference for benchmarking with ours. So, okay, about problems and limitation, because as you probably imagine, this is not something straightforward. We face a lot of problems and challenges. For example, mathematically speaking, if you want to work with Qtrits, you have to work with an 8-dimensional hypersphere. And of course, you can't put a 8-dimensional hypersphere in a quantum circuit. And more, we have non-trivial distinction between pure and mixed states in a 8-dimensional hypersphere. So that's why we try to search for another type of representation with the unit spheres. And that's how we found the Majorana representation for Qtrits, where we have, again, a trivial distinction between pure and mixed states. And we only need 4 angles, and with these 4 angles, we can encode any type of Qtrit as 2 points in the surface of the Majorana sphere using this formula. And of course, follow some steps to apply this in a quantum circuit, but with only 4 angles, you can encode any type of pure Qtrit state. So about our software and implementation, first of all, the difference between qubits and Qtrits. When you are working with qubits, of course, you have 4 Pauli matrices, but in our case, we have 8 Hellman matrices, which are this one. And now, if we exponentiate a Hellman matrix, we are not going to gain a rotation gate, at least not for a Majorana representation, because we are going to move only one of the points of the 2 that we have in the Majorana representation. This is not the case in qubits, because if you exponentiate the Pauli matrix, you can form the rotation gate. So we use these three matrices, which are combination of Hellman matrices, and with the formula in the left part of the slide, we can exponentiate these matrices and gain, again, the rotation matrices. And also, as we need Hadamard gates and swap gates in our model, the generalization of these gates for Qutrits are these one presented in these two papers, what are the same, but just the generalization for Qutrits. So, of course, we don't have access to the source code of the reference model. That's why the first step was trying to replicate the model. And this is the AUK scores that we obtain. I mean, makes sense because we didn't use a high-performance simulator, and I'm going to explain later why. So in the end, the numbers are very similar, so the performance is practically the same. So we can say that we replicate the model properly, so we can use it for benchmarking ours. More things, in the reference model, they only have two angles to encode the particle information, but in our case, as I said, we have two more angles. So we try a lot of different combinations. I mean, a lot, I promise. And in the end, we found that maintaining the two first angles as the same as in the reference model, or using the mass and the energy of the jet, or the longitudinal and transversal impact parameters, we have two very strong combinations with very robust results, as I'm going to show. So more things. In the reference model, they use the Penny Lane framework, which is one of the few frameworks we support for Qtrits simulations. And that was perfect for us. That's why, of course, we chose that reference model. But of course, this comes with more limitations. For example, we can only use the default Qtrits simulator with it a Python-based simulator. And that's why, to do a proper benchmarking, we also replicate the reference model using the default qubit simulator. Also, we are limited to only 8 Qutrits maximum in the circuit. So, as they said, they use in the reference paper 10 qubits only for the encoding. With this restriction, we can only use 4 Qutrits for the encoding, the particle encoding. So we have now 1 Qtrit for the latent space, 3 Qutrits as trash, other 3 initialized to 0 as reference Qutrits, and 1 ancilla. I mean, this is a quantum autoencoder. I don't have enough time to explain deeper how autoencoder works, but the important thing here, and what I want to highlight, is that this is a swap gate between the trash Qutrits and the reference Qutrits initialized to 0, and we are going to use this to calculate the fidelity between the trash and the reference Qutrits, and we are going to use the fidelity distribution to detect the anomalous events. So, of course, our results. First of all, the AUK scores. Again, I mean, this is very consistent. We didn't surpass the performance of the qubit-based model, but I mean, again, the numbers are very similar, and we can say that the performance is very comparable. Between the Qtrits A and the Qtrits B model, I mean, it's the same structure, the same model, only using the 2 different combinations of parameters. In the Qtrits A, we use the mass and the energy of the jet particle, and in the B model, we use the longitudinal and transversal impact parameters. But this is not the most interesting part of our results, because the interesting part is this part. And I'm going to explain first what are you seeing. I mean, this is the fidelity distributions. The blue solid part, it's the fidelity distribution of the training data, and the 3 lines, the red, blue, and green one, are the physical signals. So the first picture is the qubit-based model result. And I mean, this result is consistent with the result in the reference paper. I mean, we are not doing something bad. I mean, this is very consistent. And the two other pictures are our results. And as you can see, seems like we are gaining expressiveness in our model, and we have a more clearly trivial distinction between physical signals. So as we only implement the encoder part of the autoencoder, if we now implement the decoder, we are going to see clearly in the anomaly metrics the presence of anomalous events, and only identificate in which part of the code are anomalous events. So I mean, this looks like promising and very interesting as we are working with Qtrits. It's maybe sometimes sounds crazy and strange, but we are very happy with our results. But in the end, of course, it's a gate-based model. And if we are thinking about implementing this in long-term application in quantum hardware at CERN, this leads with some problems. For example, we have a low hardware scalability because we have to decompose these gates in basic gates, and the transpilation of SU3 operation, it's not quite trivial. And also, as is a autoencoder, a quantum autoencoder, we have an optimization process, which is a NP hard problem, as you are familiar with, and all the problems that this leads. So this is another problem to take care. And also, as we are increasing the number of Qtrits, the growth of the memory requirements increases exponentially, so we have to take care about this also. So why not? Why not? We can think about a QO formulation of our problem and maybe trying to apply annealing for the anomaly detection at LHC data. Why? Why are you thinking about that? Because we can gain a better and more natural scaling, trying to avoiding the barrier plateaus, and instead of analyzing a specific part, we can make a globally analysis, and also we can fragmentate our problem and even introduce particle physical constraints. And applying annealing, we can search a solution which maximize at the same time the fidelity inside the real hardware. Maybe we can improve our model and enhance our performance. And these two papers are a good example because they they present a QO formulation for general anomaly detection, which, okay, it's good, but we need a unique, a specific QO formulation for LHC, anomaly detection in LHC data. But of course, we don't have this QO formulation. But in the case that we can formulate our problem as QO applying annealing, maybe we can obtain very promising results. And I mean, we can use, for example, QO formulation that they use in track reconstruction or in detector simulator. We have one specific for anomaly detection. So we are working on this. We accept help. So our conclusions. The Majorana representation, of course, is an effective representation for Qtrits within unit spheres. We obtain a comparable performance with the qubit-based model, and of course, we have a greater capacity to discriminate between signals. So, thinking about the future, well, we can think about the generalization to mixed states because now we are working only with pure states, only working in the surface of the sphere. Maybe we can improve even more the expressiveness of our model and our performance. At the same for Q-quartz, I mean higher level systems. And of course, maybe trying to create a QO formulation for anomaly detection in high energy physics. Well, the first step is qubits, of course, and then trying Qtrits. So, well, thank you so much. This is the team, Miriam, Veronica, and me, and this is our paper. And if you are interested in this topic, I really invite you to check. Everything is explained deeper. So, well, thank you so much. If you have any question.
Any questions? I guess that. Oh,
yeah. You talk about the Gell-Mann matrix, like being the version for Qutrits of the Pauli matrices. Do they work in the same way? Do they share some properties?
Yeah, it's a very interesting question. Thank you. I have a slide for that, I think. Yeah. I mean, well, the titles are in Spanish, I'm sorry, but the information is the same. Hellman matrices are like Pauli matrices, but working in a specific subspace of the entire space of Qutrits. For example, lambda 1, it's the same like X gate, Pauli X, but working only in the subspace between 0 and 1. But if you look at, lambda 6 is the same, but working in between the state 1 and 2. And this is quite interesting because if you do lambda 1 plus lambda 6 with a factor of normalization, you can create the rotation gate for the x-axis as the same of this. Yeah, okay. Yeah. I mean, sigma 1 is the result of lambda 1 plus lambda 6 with a normalization factor. So yeah, they do the same as the Pauli matrices, but only in a subspace of the entire Qtrit space.
Okay, thanks.
Anyone else? All right, I mean, I think I have a question. I'm going to come back down. Obviously, like towards the start, you gave some reasons why Qtrits are sort of like good generally. Like, you know, obviously you have kind of like more space to work with, like more information and like more maybe expressibility. Was there a particular reason you wanted to use them for like this problem? Or is it just the general sort of good qualities of those?
I mean, we try Qtrits as the first step to explore. I mean, as qubits are not enough now for solve the challenge that is facing CERN with the increase of the future increase of the use of the data. We took this as the first step. I mean, this mostly was my master thesis, so was an attempt to explore new possibilities, and now I'm completely into these possibilities in my PhD thesis. So yeah, I mean, not everything is perfect. There's some advantages, of course. Disadvantages, I don't know if I have to say the disadvantages, of course. But with talking about gate-based models, with higher number of levels, of course, we have more complex gates errors. And also, it's more complex to implementing hardware. But also, there's some papers, as I said, showing that also there's promising quantum error code. So maybe it's not the worst disadvantage that you can face. But yeah.
First of all, thank you for the nice talk. I have a question. Do you get any advantage in terms of like, if you think about fermionic representation, like to translate from fermionic representation to Qutrits representation with respect to the qubit representation? Like,
it's a really good question. I think I don't have an answer right now because I didn't explore that possibility. But we can explore in the future that case. But right now, I don't have a clear answer for that.
okay, thank you.
Anyone else? No? Okay, in that case, let's thank our speaker again.